in three parts. First, number one, you've got an assignment where you're going to analyse and critically evaluate methods of AC and DC motor control. I haven't given the assignment a good look over from last couple of years yet, but I'm unlikely to change it a great deal. A likely thing is to be given an application to have a look at, to analyse that application and what its needs are, motor and drive wise, and suggest and justify a solution. Alright, so that'll be what that is. And normal thing is I give about 3 weeks for that to be completed, handed in online in the normal way. Assignment 2 is an investigation and critical evaluation of further applications of power electronics. In the past I've picked a range of different things, DC converters, induction heating, to look at induction heating of bearings for fitting them on shafts and that type of thing, and how those systems work. Again, there'll be an assignment, bit of working class, bit of guidance as to where to look for information. Beyond that, that'll be research it and suggest a solution or, for a particular problem. Yep. And then the third part of the assessment is at the end of the module, you'll have a 2-hour examination that assesses your ability to analyse three-phase power distribution systems. All right. Outline plan, and it is an outline plan, and I'll tell you why it's outline. All the other 2 years I've taught this over both semesters, shorter sessions, and that's very different to teaching it in 3-hour blocks. So I'm toying around with how I'm going to fit everything in, and my current plan is after this week to maybe split the session between a little bit of power systems analysis and some calcs, together with some work on motors and drives and bits and pieces. And then towards the end of the module, when the 2 assignments are finished, we'll do the analysis of power systems all for the whole session. Probably will, at an appropriate point, not the same time every week, we'll break away and have a coffee for 15-20 minutes and come back, okay? But other than that, we're here till 3:15. So, let's start having a look then. Power in single-phase AC circuits. If we apply a single-phase, if we put a sinusoidal voltage, it's lowercase v brackets t, meaning instantaneous value of a sinusoid, to a single-phase circuit, we would have a sinusoidal current flow in that, okay? And we could calculate the instantaneous voltage at any time with the formula Vm for the maximum or peak voltage multiplied by the sine of the frequency plus or minus any phase angle. And we could do the same with the current. For either of those two formulas, Vm or Im as the peak current or voltage respectively, omega is the angular frequency in radians per second. The other way of expressing that in terms of the frequency in hertz is that omega is 2 pi f. And that should be familiar from other studies, hopefully. Okay? And in each case, theta 1 is the angle or phase angle of the voltage in radians in this case. So if you're if your frequency's in omega, then your angle needs to be in radians, and theta 2 is the angle of I in radians. Although generally you'd be dealing with one of those as being no phase angle, and the other one, what phase angle is it to usually the voltage. Yep. So generally, if you're doing a multiplication of those two, or using both of those, one of them will be an in-phase component with no angle added or taken away from it. Alright, everyone okay with that? Right, gents, moving on from that, consequently, as power, one way of calculating power is the voltage multiplied by the current. We can calculate the instantaneous power at any moment in time by multiplying together the instantaneous voltage and the instantaneous current. Yeah. So, gents, if we want to know the instantaneous power at any moment in time, we multiply the instantaneous voltage by the instantaneous current using that formula, and we can find out what power is being drawn or used by that circuit at any moment in time. So, if we look at that, I want to talk about a term called active power, that measured in watts. If we apply an AC voltage to a load that is purely resistive, in nature, current and voltage are in phase with each other. They will be in phase with each other. No phase shift in that circuit. So in this graph here, the blue waveform is the voltage waveform. The red one is the current. Yeah, and there's no phase shift between them. So every time the blue one crosses zero, the red one is also crossing zero. When the blue peaks, the red is peaking, and so on. If we calculate the power instantaneously all the time through those two waveforms, we get 2 power pulses for every 1 cycle of the mains. Yep. The other things that you need to be aware of, so we got the power pulses are twice the frequency of the supply. The other thing you need to be aware of is, in the formulas on the previous page, Vm sine omega t, that Vm is the peak value of the voltage, peak value of current if we're talking about Im. Power is calculated from the effective or RMS values of those voltages and currents. Okay, so to get the RMS value of voltage, you take the peak value and divide by root 2. It's the effective DC value, yeah. It's a value that would be I'll put it on another slide in a minute, Joe, alright? But you're correct, it's the equivalent DC value of that AC sine wave, okay? It is only root 2 for a perfect sine wave. If the waveform was a different shape, it wouldn't be E peak of a root 2. It would be a different formula for that, okay? And a RMS current is the peak current of a root 2 as well. Okay, So if you've got an RMS value, you multiply by root 2 to find out what the peak is. So to be very careful when you're reading a question as to whether that's talking about the peak value or whether you're talking about the RMS values. And if you're given a voltage in this form, it must be talking about that being the peak. Yeah. If you're told the effective value, you're being given the RMS value. Okay? Because that's the waveform, and this is peak. RMS, if there's 0 along there, RMS is root 2 times the peak. It's a DC equivalent value and is a straight line. So when they say the mains from these sockets is 230 volts nominally, that's the RMS value. It's the value that would give the same power in the same load as the same voltage DC. Yeah. That's the yeah. Hang on. Peak over root 2. This value here is peak over root 2. It's got to be less. Yeah. I mean, you've got a bit of -1, a bit of +1 added together to make it. It gives you the useful power from that system. Okay. Now, a useful practical point to this is cheaper digital meters measure average voltage and current and convert it to RMS. But that conversion process is only good for a per sine wave. So if you're using it on any other shaped waveforms, you won't be getting a true RMS reading. To do that, you need to spend about 2 or 3 times as much money on the meter to get a true RMS meter that actually measures the RMS value and not an average converted. Okay? I'm not up to date with the current costs of instruments, so I don't know what the difference in price is, but there always used to be a considerable difference. When I was in the industry, you probably had to pay £700–800 for a true RMS multimeter, good quality one. Is it not? Yeah. Okay. Yeah. All right. You only spend that money if you need it, really. So, moving on from that, then, we need then to talk about what we mean by something called reactive power. Yeah. And 2 types of that. The first one is where the load is inductive, and we'll talk first about a load that's purely inductive. There is only an inductance. We assume it has 0 resistance. I've drawn 2 phasor diagrams representing that circuit. The first one is the phasor difference between the voltage of the supply and the current flowing in it. And anyone remember what the word is to help you determine? Civil, yeah. C-I-V-I-L. In an inductive circuit, so we're just looking at that half, current is after or lags the voltage. And we always talk about these phasors rotating in an anti-clockwise direction, therefore the current is behind the voltage here. Or we could equally say the voltage is leading the current. So current lagging voltage or voltage leading current is correct for that circuit. Okay. We also can draw a phasor diagram representing the active power in that circuit. The reactive power for an inductive circuit, or the reactive power, uses the symbol Q, And here we're talking about Q for the inductor, so we talk about QL. What it's doing is it uses power, the reactive power being used by an inductor is the power used to magnetize or create the field in that inductor. So it's creating a field in one direction and then passing it back and then creating the field in the opposite direction and then passing that back. So when you connect an inductor to this circuit, in 1/2 cycle it's drawing power away and then putting it back, and then it's drawing power in the other direction and putting it back. Doesn't actually do any useful work in that inductor. No heat, no change to any mechanical movement at all. The reactive power does not do any useful work. Everything taken from the source is given back again. Yeah, no useful work done. And you can see from the same type of diagram, here again, the blue waveform is the voltage, the red one is the current. When we multiply all the instantaneous values of those together, we get a power pulse in green that's got 1/2 of the cycle negative, the other half positive. Therefore, in this section, if we consider there and there, we're taking power from the source. Don't really matter which one you call taking it. You could call the other one taking it. Wouldn't matter. In here, we're giving it back. And in there, we're giving it back. So no overall power in watts is being used or converted into another form, because that's what electricity is about. We take electricity in one form, we convert it to a useful form like a motor turning or a heater heating up or a light emitting coming from a light. Yeah, none of that is happening in this type of circuit. The waveform shows that for each power pulse there's one matched by a -1. No electrical power is converted to useful power. Inductive loads are said to absorb reactive power, QL, from the source. Okay, so the general term is that they actually take a positive reactive power. Reactive power also, good point, is measured in VAR. VAR, that term is short for volt amps reactive. So it is still the product of the current and the voltage, but they are 90 degrees out of phase with any resistive current and voltage, represented by this phasor diagram here. So this sign it absorbs, or as a positive use of reactive power, means that we've got a positive phasor for it. It's pointing 90 degrees upwards. And that'll become a little bit clearer of that when we've covered the other reactive power, the capacitive reactive power, in a minute. Right, is everyone okay with that?
Say, for example, you're using that coil to do some mechanical work. Is that going to cause a phase shift? Say, for example, in a solenoid, would that cause a momentary phase shift?
If that coil is what we're modelling here, an absolutely pure inductor, i.e. Henry's only and no ohms, which is not achievable in real life, okay, then you would get a 90-degree phase shift between voltage and current, as shown on this diagram here. They're actually, as the voltage crossing zero there, the current crosses zero 90 degrees after it. Yeah. So the current is lagging 90 degrees behind.
No, I'm sorry, I'm thinking if you actually put a roof on the magnetic field.
Yeah, well, yeah, we're going to come to that a bit later, but once you once you add a resistor in there, I don't want to do it on this diagram, but we'll come to that later, you then don't get a perfect, you've got a 90-degree component, a 0-degree component, and you've got a resultant between the two. We ain't got that far yet. Okay? So you've got two currents out of phase with each other.
Yeah.
Yeah? Alright? So, hang on. Couple of more bits to talk about that situation. Yeah? There's a number of ways that you could find out what the reactive power absorbed by the inductor, QL, is. You can find it from the generator voltage, in this case, the product of generator voltage and the inductor current. Yeah. You can find it from the inductor current squared multiplied by the inductive reactance, and we've got XL we can get from omega L or 2 pi FL. Yeah. And you can find it from the generator voltage squared divided by the inductive reactance of the coil. And transformer data sheets will tell you things like what the inductive reactances are and bits and pieces, and either that or things can be measured. But generally you're going to be finding it mostly from a voltage and a current. The other type of reactive power, okay, is where the load is purely capacitive. Again here, the load is purely capacitive. The current leads the voltage. So if I write the word civil up here again, but we're looking at a capacitive circuit this time, this half. In a capacitive circuit, the current is ahead of the voltage, it leads the voltage, or you could say the voltage lags the current. So in our phasor diagram here, drawn around that way, the current here is ahead of the voltage here. Or we can say the voltage is behind the current. When we draw the phasor diagram for QC, it is a negative phase angle of 90 degrees. We're going to be doing some calculations that will involve us using complex numbers. That would be, for QC, you'd be using a negative J term within that formula work. In terms of QC, a positive J term with the inductive side. And I have asked, after this session, they've still got the advanced math support with Mark, okay? And I have asked him today to do a little refresher on complex arithmetic. All right? Again, this reactive power QC is measured in VAR, short for volt amps reactives. It's got the same units as the inductive one. And overall, when we look at whole circuits, we're going to be interested in the difference between those two. So you're going to have a negative, you're going to have a positive reactive power, and if you've got capacitance as well, a negative reactive power, and the overall reactive power in that circuit is going to be the difference between the two. But more about that later, possibly next week. When we plot the waveforms for this circuit, again, we've got the current in red, the voltage in blue, okay, but this time the current is peaking ahead of the voltage by 90 degrees. Our power pulses again have got positive and negative sides to them, but they're the opposite way up to what they were with the inductor. The inductor went underneath first and over the top second. Alright, so here the capacitor is charging there and there, and here it's charging up the other way. So it charges, discharges, charges in the opposite direction, and does that twice per cycle. Overall, again, no real work is being done. Apart from charging and discharging it, there is no resistance in this theoretically capacitance only circuit, so no work can be done. No power in watts is being used. Capacitive loads are said to supply reactive power, QC, to the source. So you've got to choose a direction for each of the two different ones. So somebody's arbitrarily said inductors draw reactive power from a source, capacitors give it back. Yep. In reality, when one is drawing, the other one's passing back and vice versa, because a capacitor's got to charge up, so as an inductor's got to charge its field. But when the inductor's charging its field, the capacitor will be given some charge back again, and vice versa. Yep. If there's both in the circuit. Quite often in industrial systems, you ought to probably know that there usually is, in the form of some power factor correction capacitors. Yep. So, again, a little bit more about these phasor diagrams and how you can calculate values for QC. We can get it from the generator voltage times the capacitor current. We can get it from that current squared times the capacitive reactance, XC, and we can get it from the generator voltage squared over XC. Again, XC can be calculated from 1 over omega C, or from 1 over 2 pi times the frequency in hertz times C. Always bear in mind capacitance values in that formula are in farads, even though they're likely to be values in microfarads times 10 to the minus 6. Alright. So, we need to have a clarified distinction, really. This is to clarify everything I've covered so far, in a way, between active and reactive power. First of all, one cannot be converted into the other. They function completely independently of each other. You can't convert power in watts into vars or vice versa. Okay? They can be treated as separate quantities in electrical circuits. So when we're doing calculations, we deal with Q and P and another an amount called the apparent power, which we'll look at in a minute, which is the combination of the two. They're treated as separate quantities. Both of them, despite not doing any useful work, place a burden on the transmission lines that supply the equipment. Because when the inductor is charging up and drawing current, that current's got to flow down a transmission line and back again, and so is the current charging and discharging the capacitor. Therefore, this reactive power is drawing current backwards and forwards despite not producing any useful heat, light, or mechanical motion. Active power produces a tangible result in the form of work done. So the watts does. It produces heat, light, or mechanical motion. Reactive power does no useful work. It represents energy that oscillates backwards and forwards between its magnetic field and the source in the case of an inductance, or between the charge on the capacitor and the source in terms of a capacitor. A large system such as a factory or a oil rig or wherever it is you work, quite often, invariably really, presents a large active reactive load in the form of heaters, motors. As soon as you wind a coil, you've got an inductor, even if that's just that loose coil on a 3-bar electric fire or something. You've got some inductance there that's going to cause some reactive power. They draw reactive loads, and they do that to sustain the magnetic fields. So in transformers, you've got to sustain a magnetic field. In a motor, they wouldn't work without a magnetic field. Okay, so active loads provide heat and mechanical energy. So what we need to do then is consider loads that absorb both active and reactive power combined. Yep. So ones that include both. What happens when we get both of them in a circuit? That's what we're going to do now. So if we come up with a circuit where we've got a, and that's what you were on about, Bob, wasn't it? When you connect a load, was it you?
Yeah,
You connected a load now, a resistor, across the inductor. So we've got a current flowing through the resistance, and we've got a current flowing through the inductor. Okay? In that case, we've got a combined current voltage phasor diagram. Here's E. This board is getting on my nerves. There's E. And I've just moved it down a little bit so you can see the second arrow. But that one there is representing the resistive current that is in phase with the supply voltage. Here, if we use the word civil, and we're looking at that side, the inductive current lags the voltage by 90 degrees. So this here is representing IL. Okay? The line current, that's this one here, is the resultant, or the total current in the circuit, is the resultant of those two. And as you can see, it draws that current out of phase with the supply voltage. They're not in phase with each other anymore. So we've got a current IR in phase with the source voltage, whilst IL lags it by 90 degrees. The current drawn from the source hence lags the supply voltage by an angle theta, and that angle will depend upon how big the inductive current is to the resistive current. If we make the inductive current bigger, it's going to pull the angle down and make the current drawn from the supply bigger and the line longer. If we make the reactive current smaller, it's going to make the angle smaller. Right? The phase angle between the two. The waveform now shows two positive areas representing the real power in watts. So these two above the line in blue there represents P in watts. These two small bits down the bottom here, there, and there, their size again will depend upon the relationship between how much in phase current and how much out of phase current we've got, i.e. the difference between the reactive and the active currents. But those two red bits down there are the Q measured in VAR. So this bit is using useful power. That's the inductor giving back power to the source, reactive power to the source. So these are active, they're reactive. Sorry, Alan, no problem.
Yeah, sorry, mate.
Looking a little bit deeper at the combined situation, the magnitude of the current drawn, I, drawn from the source, from this phasor diagram, can be determined using Pythagoras' theorem. So we've got a triangle situation here, where we've got an in-phase current, IR. We've got an out of phase, 90 degrees out of phase current, IQ. And we've got a line current, IL, that is the hypotenuse of a right angle triangle. It's quite easy, if we know any two of them, to use Pythagoras' theorem. A line current I is a square root of IR squared plus the square root of IL squared. So all that trigonometry you done at school and everything is useful in electrical. It is in mechanical as well for forces, isn't it? So the magnitude of the angle, theta, depends on the value of the inductor. And the value of the resistor as well, really, because that's going to affect the in-phase current. Consequently, the larger this angle is, the greater the current required to produce a given amount of power. Yeah. So, for a given resistance there, that's going to give us a given amount of power. If we get a much higher inductance level, a much higher reactive power being drawn from the source, that phase angle is going to be wider, and therefore if we make this phase angle here a wider one, up there somewhere, the length of that IL line becomes longer. It's drawing more current from the source for the same amount of resistive current, and therefore the same amount of power. The voltage doesn't change. Yeah. So we still get the same amount of real power dissipated, the same amount of heat out of it. It's going to cost us more in current, which has implications, and we're going to have more about that shortly. Yeah, it's cost implications, certainly does. All right. Any questions? So, we've looked at real power, we've looked at apparent reactive power. Well, now we need to consider what is the resultant of those two, the apparent power in the circuit. Uses the symbol S, and some of you might have noticed that transformers are rated not in watts, but in VA, volt amperes, or kVA. Or if they're really big ones, MVA. It is the product of the line current and the line voltage, volt amperes. So the combination of real and apparent power produce a resultant. So here's our apparent Q here is our reactive power. P is our real power in watts, we get a resultant between those, S, in volt amps, and there's a phase angle between them. So we can calculate S by multiplying the line voltage by a line current, or from the power triangle, square root of the power squared plus the reactive power squared. The apparent power forms an angle with the real power, theta, that is the same as the angle of the lagging current produced by this circuit discussed earlier. Alright, so you can get the phase angle and effectively the power factor we're going to talk about shortly from either the relationship between the angle between P and S, or from the angle between the currents, the actual line current and the current due to the power. That angle works out to be the same from either triangle. Alright, any questions on that? So, reactive loads and power factor. Many reactive loads on a system that require reactive power Q to set up the magnetic fields. They include motors, transformers, heaters, welding plant, X-ray machines, dozens of things in a factory industrial situation taking reactive power. If we have a high reactive load, the left-hand diagram, Q is relative to P is quite large. It means the supply lines have to carry more current, because if we assume voltage stays the same, then if that line is longer, the current must be more, okay, at a given voltage to provide the same amount of power. So if in those two diagrams we assume that the power line is the same length, the left-hand one draws more current from the source than the right-hand one does, because the angle is less, the reactive power is less, and hence there's less current being drawn to create that VA line the same length across the top there. So a lower reactive load means less current is carried in the supply line to deliver the same amount of usable power in watts. The S line of the triangle is shorter. Alright? Yep. Which leads us on to what we mean by power factor. That left-hand triangle is termed a circuit that's got a low power factor, the right-hand one, high power factor. Power factor for a particular load or combination of loads, in a week or two, we're going to look at how we can actually do calculations using PS and Q on a number of loads that might be connected to one generator all in one go, and just by separately considering all the power bits, all the QL bits and all the QC bits added together to do a combination calculation on a load center, if you like. Okay, so power factor is the ratio between the real power in watts and the apparent power in VA. It is the cosine of the angle theta. And if you look on some big distribution centers, they'll have a meter telling you what the cos theta is or what the power factor is. And if a power factor of unity or 1 is an angle of 0, so it's a perfect non-reactive load. Generally don't get to that in an industrial situation, because once you get beyond a certain point you don't get the payback on the amount of capacitance you have to add to get rid of any more reactive load. So our power factor is the cosine of this angle, or we can get it from the ratio between S and P. I've recovered that now. So just moving on, implications of poor or low power factor. We already discussed these two triangles and that we get more current, need more current where we got a low power factor than where we got a high power factor. A transmission line, like the national grid for instance, can only carry a finite amount of current for a given cable size and pylon size and everything. Because a low power factor results in more current being needed to produce a given amount of real power in watts, okay, less useful energy can therefore only be transmitted on that line if you've got poor power factor. For that very reason, that leads to supply companies penalising the ones that own or supply the transmission lines, that penalise larger consumers for poor power factor. And they do that through the tariff. What they do is they base, or they make a charge, a monthly charge, dependent upon your maximum demand in kilovolt amps. So if I remember back, I used to check this when I worked at Fibronal, and they'd record what the maximum demand was each week, and they'd keep an eye on it. What they were in, that was a meter that had a needle on it in them days. You know, the types of things where I'll push a maximum marker up beyond where it was before, so when it falls back, probably electronic now, but they'd have a meter that indicated in that month what your maximum demand was. I think you used to take a reading of demand every so often or something like that, and then record what the highest was. And they'll then make a monthly charge based on that highest demand. And I had a little search on the internet, and I got a table for electricity company on the island of Jersey of all places. But on a low volt, just as an example, on a low voltage 230 400 volt, and make a maximum demand charge of 820 pence per kV kilovolt ampere of maximum demand. Yeah, so that's 8 quid per kVA of maximum demand. So you've got a maximum demand of 100 kVA, that's 800 quid a month they're charging you on that maximum demand. If you're a high voltage user of electricity, if you were to take your electricity at 11 kV, the cost for maximum demand is slightly less. But then they're going to be getting more out of them anyway, because likely their load is significantly higher. The implications here are is you don't really want lots of motors all turning on at once, because that could potentially stick your maximum demand up. Either that, or you want some local power factor correction to make sure that they don't do that in the first place. So there's two ways of doing, we didn't discuss power factor correction yet, there's two ways of doing it. One is to have it overall on the load centre where your switchboard is. The other is to have it locally, power factor correction mounted actually on at the local point where the motor is, and sometimes both. Usually the load centre stuff is automatic, so it'll switch in and out according to the changes in reactive load. But we're going to discuss power factor correction possibly next week or the week after. Alright? But what I'm trying to give here as an indication, and there's a question in the tutorial questions that looks at the difference in that cost if you improve the power factor by a certain amount. It's quite significant and important for people that are paying for the electricity. So before I give you the tutorial questions, I'll just put a quick example up on the board so we can run through one and just clarify where the results might or could come from. So I'll give you a couple of minutes to write that down. A 400 volt motor rated at 4 kilowatts draws a line current of 15.6 amps. Find the apparent power S, the reactive power Q, and the power factor. Look like we find that. Right, gents, so how can we go about doing that? How can we go about finding apparent power? Yeah, that's VL, the line voltage which you've been given, times the line current, the current that's drawing, because you're measuring that with an ammeter, for instance. So simply the 15.6 amps multiplied by the 400 volts. Someone will push some buttons for us, I suppose. 6240 volt amperes. Yeah. And up here, what I'm going to start to do, I do recommend that you do this in these types of questions, is build your right angle triangle so you can see where everything goes. We now calculated S. I'm going to put the calculated values in red. That's 6240 VA. Yeah. Reactive power Q. How can we calculate that? In this instance, Pythagoras theorem. So that's going to be the theorem actually rearranged a little bit. It's going to be the hypotenuse squared, take away the power side of it squared. So that's the root of 6240 squared minus 4000 squared. Again, expect someone will push some buttons for us.
4789.
4789 units. Daniel, oh god, that's all right. VAR, yeah. Four, 7, 8, 9. It stands for, it is volt amps, but the R is representing volt amps reactive. Okay. On real power system, we're quite often here going to be talking about kVA, kVAR, and kilowatts. And if you've got all of those three quantities in K, you can just put the numbers in and the answers in K. So if you've got the power in kilowatts and S in kVA, you can just put the numbers in and you'll come out with Q in kVARs. Yeah? C, a power factor. How are we going to calculate that? Yeah, it's P over S, because it's the cosine of the angle. Yeah, cosine is adjacent of a hypotenuse. That's the 4000 over the 6240, which is and that's a ratio, so I ain't got any units. .641. Not untypical for a power factor of a motor. 0.6 could be 0.4 and 0.7. Yeah, so that's not untypical at all. All right. I'm going to. Right, gents. So with our mathematicians covered the complex arithmetic with us, now what we're going to do today is have a look at some AC network analysis. We're going to look at initially at inductive reactance and how it varies with frequency. Do some calculations with a series, a parallel R-L circuit, a resistor inductor circuit. Do the same with capacitive reactance and how that varies with frequency. Most of that is a little bit of revision really from science. Calculation with a series and parallel RC circuits. Then we'll look at putting all three components in and analysing an RLC circuit. And through all of that we will prove that all the laws we've already dealt with in terms of Kirchhoff's laws, Ohm's law and everything still apply in an AC circuit. Remembering that when you're analysing you are looking at a snapshot or an instant in time. So although in an AC circuit the voltage is constantly changing when it hits at peak and the current is changing, every moment in time you could apply Kirchhoff's law and it would apply around that circuit. You could apply Kirchhoff's current and voltage laws and they will always apply. And then finishing up, and hopefully we'll get all this done this week, if not we'll finish up next week before we move on, because we'll have a look at how we can use Thevenin's theorem that we've been learning with DC circuits, just if we can apply that to an AC circuit. Okay, so that's the plan anyway. So, reactance and impedance in AC circuits. As soon as we switch to AC, we should talk about what we've been talking about as resistance, or the opposition to current flow. And it's best to think of resistance like that. It's the opposition to current flow. The more resistance we got for a given voltage, the less current we get. We should start to call it really impedance. It's got a symbol Z, still measured in ohms, but it becomes a complex quantity in terms of it's now got a magnitude and an angle associated with it. Okay. If we have pure resistance in a circuit, no reactive components that we're coming on to in a minute, so like this, an AC source, an AC current will flow, we'll get a voltage across a resistor. If we draw what's called a phasor diagram of that, where the red is the phasor diagram, that phasor diagram, the red line is representing the current flowing in the circuit, the blue line the applied voltage. Okay, they're drawn, should be over top of each other, but I've just separated them on the diagram on the board so that you can see the length of both of them. So the length of them represents their size, and then the angle between them is 0, because if there's only resistance in the circuit, current and voltage are in phase with each other. The voltage and current peak together. There, like that, and the voltage and current cross the 0 line together in time. Okay, so if we have resistance only, the current and the voltage are in phase with each other. There's no angle between them. We pass those ones round, they're the slides that I've got up on the board. Oh, did you? Oh, sorry, Mark. I must have. They looked a lot less. None of the diagrams in them, are there? Oh, well. Yeah, should be. I thought they were. Anyway, so I'm sorry. Never mind. Don't worry. I'll give you some time to take them down. And actually, most of this stuff is in the note pack that I've given you as well. Alright? So, current and voltage in phase. If we look at the power all the time is a multiplication of the instantaneous voltage and the instantaneous current. So we get two positive power pulses with a resistor. Okay? We'll come back to the power shortly. So resistive circuits, you can really just deal with them like you would a DC circuit, because there's no what's called reactive component. Voltage and current are in phase. Ohm's law, Kirchhoff's laws, etc. apply, and you can just deal with it as though it was a DC circuit. Alright? The complication comes when we add some kind of reactive component to the circuit. Inductor. Okay? The instantaneous voltage across an inductor, EL, is given by EL is the inductance in henries, that's L, multiplied by di by dt. What is di by dt? Andrew, got any idea? It's a differential. So it's the, what is the differential? How would we say that in words? Do you remember that it's about the rate of change of something with some other variable? So what that bit is, there, is the rate of change of current with time. Yep. So what happens in this inductor circuit is that there's an induced voltage across the inductor that's and that's at its peak when the current is changing the most. So when the current has fallen, that's where you get the biggest voltage. So the current slope is 0 at this peak here, so we get no voltage. The current is changing, di by dt is at its highest when we cross the 0 line, therefore we get the biggest voltage at that point, and it's negative. That's where there should actually be a minus sign in front of that, I believe. Okay? Because what happens is the impedance that you get for an inductor is because the voltage generated across it opposes the current that's causing it to happen. Yeah. So as it becomes a reactance, and it's frequency dependent as well, because the faster we make the change, the more voltage we get. Okay. So we're not now a simple quantity, we've got a complex quantity. Because in this circuit, if we say the current here on the phasor diagram is at 0 degrees, the voltage is 90 degrees ahead of it. We talk about going round this angle circle anti-clockwise. Yeah. So if we think about these two vectors going round in a circle, the voltage, EL, is ahead of the current. Can anyone of you remember from science the word that helps us decide whether current leads or lags voltage? Because if we look at this diagram here, the blue one is E, this is time, the voltage peaks before current peaks. Therefore we could either say voltage leads the current, or we could say current lags the voltage. Confusing, I know, but either of those would be correct. And the word that we used in science, I'll do it on a new page. L. CIVIL. This represents inductance, okay, and in an inductive circuit we'd think about covering up the C and I, forgetting about that bit, and in an inductive circuit voltage is ahead of or leads the current, or we could say current is after, lags the voltage. In a capacitive circuit, which we're going to look at in a minute, we forget this L up this end and this I, we forget them bits, and we say in a capacitive circuit current is ahead of or leads the voltage. We say voltage is lagging the current. Yeah, so that will always apply. We get a situation when we've got both of these things in the circuit, but there will always be one that's bigger than the other and make the overall circuit overall capacitive or overall inductive. Both will have an effect, as you'll see later, but one will always be bigger than the other, and therefore the circuit will either be overall capacitive or overall inductive. And we'll look at that later, and that's another little way to understand whether your circuit and the result you get is correct. You know which one of those is bigger, which got the bigger reactance. Am I getting a result that complies with civil? Okay, so that word is really handy. So in this inductive circuit, if that was a pure inductor, and you can't get one in real life because an inductor is a coil of wire, the coil of wire's got some resistance as well, okay, but if you could get a pure inductor, there would be a completely 90-degree angle, phase angle, between current and voltage, a positive 90-degree angle. That's that there. Okay, everyone happy with that? So if that voltage was 6 volts, we'd say 6 volts at angle 90 degrees. That's how we would write it. Yeah. The current might be 2 amps angle 0 degrees, and that's how you write it. You put the size of the quantity with its units, followed by the angle sign, followed by the angle in degrees or radians. Yeah, if the degrees symbol is missing, the implication there is that that's radians. Okay. So that's what's happening. So for an ideal inductor, the current lags the voltage by 90 degrees. Equally, we could say the voltage leads the current by 90 degrees. If we look at the power in such a circuit, what we get is we get a positive half cycle here and a negative one there, then a positive and then a negative. And the actual overall power dissipated in a pure inductor is a straight line 0, because all of those, in that part we're dissipating some power, in that part we're giving it back, then we're dissipating, then we're giving it back. Everything, an inductor uses no useful power at all. It does not convert energy into heat or anything like that. You can only get power from a resistance. Okay? Everyone happy with that, yeah? There's our civil. We might come back to that in a minute. Inductive reactance. So we've got this effect. The inductor causes the out of phase relationship. And the inductor has an impedance Z, where its magnitude is the inductive reactance XL. So the size of the impedance is XL ohms. So if we're going to talk about that, we would add the J to make it the impedance, then it's got its angle. Okay. So XL is the positive real part of an impedance. And you can calculate XL in one of two ways. 2 pi times the frequency times the inductance, or omega times the inductance. Omega, whenever you see that in an electrical circuit, it is always equal to 2 pi f, and its units are radians per second. It's called the angular frequency of the circuit. And quite often, it's in fact, the biggest majority of the time, it's easier to work in omega initially and only use that formula if you want to know what the frequency f is in hertz. Because it just takes pi out of the equation. Yeah. Makes the numbers less difficult. So if you can, if you're given that in omega, if you see a value something times pi, it means it's in omega. What you do have to be careful of there is you're then going to have your calculator in radians mode when you've used your angles. Alright? So, if we look at because of this frequency in here, that value XL is frequency dependent. It goes up and down with frequency. An inductor, XL rises as frequency rises. So what this means for your electrical circuit is at 60 Hertz, a 10 millihenry inductors would measure 3.77 ohms impedance. At 120 Hertz, 7.54 ohms impedance. 2500 is 157 ohms. So as you increase the frequency, the resistance or the opposition to current flow in that inductor goes up. What's going to happen to the current? Down. Yep. So as you increase frequency in an inductor circuit, the current's going to fall. And although there's a lot of maths in this, try and get an understanding of the underlying electrical principles of what happens when we change things in AC circuits. So that's what's happening. As we increase frequency with an inductor, we actually increase its impedance in the circuit, therefore the current falls. Oh my god. So, if we look at a typical circuit, we've got 10 volts at 60 Hertz, an inductor of 10 millihenries. We can find out that XL is equal to 2 pi FL, do the calculations, 3.77 ohms. Therefore, the current flowing is given by, and this is just the magnitude of the current, we've not used any complex numbers here, E10 divided by 3.77, 2.65 amps. Okay. If I wanted to add the angles to these, what would I add? I've quoted 10 volts, 60 Hertz. What do you think the angle is we use there? If you're not given one, the only thing you can do is assume it's 0 degrees. Yep. What's the angle for XL? Can you remember from the previous slide? Yeah, the angle 90 degrees. I need to orient this board. Yeah. So now doing the complex arithmetic, 10 divided by 3.77 is still 2.65 amps. Angle, and then how do we do this? Naught. How do we do? What do we do with the angles when we're dividing two polar complex numbers? We take the bottom one away from the top, so it's minus 90 degrees. So the current in this circuit is lagging the voltage by 90 degrees. Does that fit with civil? Inductive circuit, current is after, lags the voltage. Okay? That's where I said that's a useful check to be able to do that. Is make sure that your circuit fits and is complying with this when you're finished. Because if you make a mistake with one of your angles, you could be out. If we use the complex arithmetic, we do 10 angle 0 degrees divided by 3.77 angle 90 degrees, because the inductor XL has got an angle of 90 degrees associated with it. Yeah, always. And we still get the 2.65 amps, but then we say that's got an angle of minus 90 degrees, and that fits in with our word civil, because in an inductive circuit the current should be lagging the voltage. Yeah. So there it is on the next slide. Okay. And if you convert that, so if in your calculators just convert 3.77 angle 90 in polar form to rectangular form, and you should get 0 plus 3.77J, because the inductance is all imaginary number, all the unreal part. Okay. Yeah. So, if we then introduce a circuit where it's got, and this is where we'd always have this with a real inductor anyway, because it's got some resistance. So if we model a real inductor by saying this is a 10 millihenry inductor where the coil resistance is 5 ohms, for instance, they're in series with each other. We then get a more complex phasor diagram. In a series circuit, there is only one current because they're in series. So generally, you would make the current what's called the reference phasor, or the one with 0 angle in a series circuit. And then you would say what are the angle of the voltages from that 0 current. So you'd say the voltage is leading or lagging the current in that circuit. So we got our current phasor in red there, and then the 3 voltages. So we got the voltage associated with the resistor. Magic pen, turn the magic pen off. Told you, Mark, didn't I? ER. We talked about that being in phase with the current. So that's this one here. We've got the voltage across the inductor, EL. 90 degrees upwards, leading the current by 90 degrees, which it does in an inductive circuit. Yeah, think civil. And then what we get from that, if we make that into a parallelogram and draw the vector to that point, we end up with ET, the applied voltage in this case, or the resultant voltage for that vector. Yeah. So we got a voltage applied that's out of phase with the resistive voltage by 37 degrees. We'll find out in a minute. Okay. Because what we can do, and I've done this a little bit in the notes, is create a table and then fill in what we know and calculate all the other results. So we know we're applying, for instance, 10 volts and 10 volts plus 0J ohms. Okay. 10 angle 0 degrees. The impedance of the resistor Z is just 5 ohms, 5 plus J, 5 angle 0. So I've put them in both forms in the table, just in case we need them. The capacitive, why have I got C in there when I'm talking about an inductor? This has gone wrong, severely wrong. I'll cut that bit out of the video. So this is actually the impedance of the inductor is 3.77 naught plus 0.77 J or 3.77 angle 90 degrees. That's how we would express that. Okay. Now, to calculate the total impedance of this circuit, what impedances have we got in that circuit? How do we normally calculate total impedance? We've got an R and we've got XL associated with this. If they were two resistors, how would you calculate the total resistance? You'd add them together. No different with this. The total impedance of this is the resistance 5 plus 0J added to 0 plus 3.77 J. Yeah, it is in fact R plus XL J ohms. Yeah. So that equals 5 plus 3.77 J ohms. These numbers must have units as well, gents, by the way. Now we're in talking about, earlier when Mark was working, you just talk about numbers. Now we're talking about electrical quantities. They must have units. So in the rectangular form, the units go on the end. In the polar form, the units go in there. Yeah. Okay. I've got on here. So that's what the total impedance is in that circuit. Okay, so we can put that in here. 5 plus 3.77 J ohms. Do convert that to polar as well, gents, please. .3 ohms, angle 37 degrees. Yeah. Okay. So now we've done that, we've got a voltage, or we've got a current, we've got a resistance. We can find the current, can't we? It's going to be that voltage. It's going to be Ohm's law. E divided by I. We need to use them in complex form. So we've got them both in polar form, so we might as well do 10 angle 0 degrees divided by 6.3 angle 37. So let's have the result of that, please, gents. 10 over 6.3 is 1 amps, angle minus 37 degrees. Yeah. So the current lags the voltage by 37 degrees. Is that right? Yeah. Does that work with civil? Yeah. Does it work with the phasor diagram I had earlier? There's the voltage. Okay. What we're saying is if we shifted the voltage, so the voltage was at 0, the current would be down here. It's 37 degrees behind it. Or we could say the voltage leads the current by 37 degrees, makes no difference. Okay? You only need angles when you're talking about two different quantities and want to know what the phase relationship between them is. If you're only interested in how many amps it is, you're not bothered about the angle. If you want to know what the relationship between two vectors is, then you need the angles. Okay? So that's what we got in that circuit. The blue is the voltage E. The dashed red line is the current. And the current is lagging the voltage by, got to go through these slides, 37 degrees. Okay. Moving on swiftly, we could do exactly the same thing with parallel circuit. Okay, so what I'd like you to do is see if you can calculate. We've got a 10 volts applied. There's our voltage. We've made that the reference phasor this time because it's common to both components. We've got a 5 ohm resistor in parallel with a 10 millihenry inductor. Alright. Can you do the calculations to find the overall impedance of that circuit Z and the current flowing in that circuit? So have a go at that, see if you can make a start on that and find those values. You're going to do parallel resistance formula or parallel impedance formula, okay, and calculate the total impedance and the current in that circuit. What we got is XL is 2 pi FL, isn't it? Yeah. So that's 2 pi times 60 times 0.01 per millihenries. Yeah, that comes out at 3.77 ohms. Yep. Yeah. Yes. Yeah. So we're talking about ZT is equal to, what's the easiest thing to use here, do you reckon? Product of a sum. So we're talking about, remembering we've got to use complex quantities. So R is 5. There is no J part. L is 0 minus, sorry, plus 3.77J, and then that is over 5 plus 0 plus 3.77J. So there's the multiply on the top. So you've got multiplication of those numbers, addition of those numbers, and then eventually divide those numbers to come up with the result of that. So you've been doing that earlier, so I'll give you 5 minutes to come up with the result of that in rectangular form, and convert it to polar as well. So from this point, having multiplied the top and added the bottom, we've now got to multiply this out to get rid of the J term underneath. So we've got to do 18.85J multiplied by 5 minus 3.77J. We've got to do that on the top, and on the bottom 5 plus 3.77J times 5 minus 3.77J. Yep. And what happened here? Remember, this is always, the result of this is always the J disappear, and the result is these two, this number squared plus that number squared, a constant. Yeah. Because 3.77 times minus 3.77 is a negative number, but then that's multiplied by J squared, which is minus 1. So you end up with two positive numbers added together there. Alright? So the result of that bottom is 5 squared plus 3.77 squared. And the result of the top is a bit more messy than that. What we got then, gents, for this top line? Those two multiplied together. Plus what? Jack, say that again. Yeah. Well, I'm saying yes. I don't know. Would everyone else agree with that? Yeah. So then, what is that in terms of what is 71.06 J squared? $94.25 J, yeah? Plus 71.06 J squared. So that must be minus 71.06, yeah? plus 94.25J on the top. And what is 5 squared plus 3.77 squared multiplied out? $39.2. So then the final result of that is you split it. So you do minus 71.06 divided by 39.2. And 94.25 J divided by 39.2. So here we divide the 71.06 by 39.2 and get the real part of the result. Divide 94.25 J by 39.2, get the imaginary part. What is that if we convert that into polar form? Three. Angle 127 degrees. Does that look right? Negative real part, positive imaginary part. What quadrant's that in? Yeah. Okay. Yes, ohms. Okay. So, from that we've got an impedance 3 ohms angle 27, or if we want it in that form, minus 1.81 plus 2.4 J. Okay. So now we're looking for our current. E divided by I. So do that in complex form and find out what the current is in this circuit. So for the benefit of the video, we've gone wrong up here. That was a positive sign in here. This is negative 71. Meaning when it comes down here as positive, we end up with a plus 1.81 plus 2.40 J. That angle is 53 degrees. Where I noticed that was going back to the original phasor diagram and knowing the circuit is inductive and therefore the impedance should have a positive angle between 0 and 90 degrees. Can't go beyond the 90 degrees of a pure inductor. So the 127 degree angle, immediate flag come up there saying something's wrong here. Just see how much just missing, getting one positive or negative sign wrong can mean you get the answer totally wrong. So where are we going here then with this voltage? What is the voltage in polar form for this circuit? $10 volts, no angle, so it's 10 angle 0 degrees, and that's not, can't even get Ohm's law right today. E over Z, Z is 3 ohms angle 53. Ten divided by 3 is 3 1/3. Amps angle must be minus 53 degrees. Does that fit with civil? current lags voltage in an inductive circuit. Yep. Good.